Hello, Will Navin and other students. Um, let's start to talk about another type or a special type of one-dimensional motion, and that is well, of an object that in this case is dropped and falls through space. Now, I'm going to have us imagine a nice smooth steel sphere, and the reason that is because there's very little air resistance that acts on nice smooth steel spheres as long as they're at speeds that are, um, not real big. And for us, dropping things and throwing things around, those those um, those air resistance forces don't get too big. All right, so here's an object. Now, this, looking forward, we're going to do a whole bunch of this in the weeks to come. And that is that we'll look at an object, and we'll draw vectors that represent forces acting on objects in lots of different situations. In this case, we'll draw the forces acting on this sphere as it falls. Well, the only one is this one. We can draw it like this, and I would label that force F subscript G. That's a gravitational force. A gravitational force. All right. Now, how big is that force? Well, it depends on some stuff that we'll get to. But the deal here is that gravitational force that acts on an object as it falls through space is constant. And because of that, I'm going to say that this constant gravitational force, force E, force, yields a constant gravitational acceleration. Now, we got to be careful here. Not all objects experience the same force. You can tell by holding two different objects. And they might feel like they weigh different amounts because gravity pulls with different amounts of force on different objects. But the weird thing is that everything that accelerates under the influence of gravity only has the same gravitational acceleration. And we're going to get to why that is in a couple more weeks. But for now, my kids have seen, drop a bowling ball, drop a little tiny mass, and they accelerate at the same rate downward, even though the forces on them are very different. That's a weird one. But like I said, we'll get there. Okay, so let's describe the motion of this sphere using two graphs, a position time graph and a velocity time graph. Well, the position time graph, we've got lots of ways. I don't know. Let's say that x equals 0 is the ground. So what I would say is maybe something like this. This thing starts slow and then speeds up as it approaches the ground. It's a parabola, half a parabola in this case. Okay, and what we've also assumed is that a downward slope here, a downward velocity, or I should say a negative velocity, means downward. So what we've sort of done also is we've defined the positive direction to be upward. All right, so if we look at, say, the slope of this tangent, that slope is negative, and we're saying the object is falling, or moving, I should say, downward. All right, so here, where we draw our velocity versus time graph, well, it starts at rest and ends up fast downward, ends up with a big negative velocity. It's going to go like that. All right, and that looks curved. Sorry, it's not. It's linear because we have this constant gravitational acceleration. And here the slope is what we call g, the constant gravitational acceleration. That says slope equals g. G is the kind of special variable that we assign for acceleration when objects are in free fall. Okay? Okay. Now, this is a bit of a handful. But here's what we're trying to show. This thing is really in the way. Can you go away and be smaller? How about this? See ya. Okay. Let's look at. So this, it looks like a table. It's supposed to sort of be a graph. Really a spatial. These lines we're going to use to really indicate how far objects move. All right. And then we're going to run through 3 separate scenarios where we talk about, well, what's the velocity of an object now? What are the forces acting on an object? What's an acceleration? And now all these, right, velocities of vector, force is of vector, acceleration is of vector. So we can actually use vectors to represent these 3 different quantities. And it's going to be a little confusing, perhaps, but hopefully we can talk through it. All right, and what we're going to do is we're also going to assume that let's look at snapshots of equal amounts of time. All right, and so let's just say that in the first interval of time, these objects are going to go, check this out, group. They're going to go from here. Let's say that they fall, oh boy. Let's say that they fall, that's also bad. Let's say that they fall, let's say they fall to there, okay? So we've just sort of said in the first interval of time, they fall 1 spatial unit here, all right, however much that is. Now, in the next equal interval of time, the question is how far do they fall, all right? Well, my folks have talked about this. Just give me some space to work here. And what we talked about is for an object, if we start something at rest and we look at some equal increments of time, well, here's what happens. If we say something in the first interval of time falls a distance d, the question is, how far does it fall in an amount of time? 2t. Well, it doesn't go 2d. It doesn't just go twice as far in twice as much time. And why is that? Well, because of the nature of the relationship between position and time for an object that accelerates. And there's that relationship. Let's make an assumption that our object starts at rest. And this says, well, this is the quadratic relationship between position and time, or change in position and time. And so what this says is, if we double the amount of time that something moves for, we don't double how far it moves. What do? Well, we double it squared, or it goes 4 times as far. And if we triple the amount of time that something moves for, we don't triple how far it goes. Well, we triple it squared. So it goes 9 times as far. In 4 times as much time, it doesn't go 4 times as far, it goes 4 squared as far. There's that quadratic relationship. And so what I'm going to try to do first is, put that information, or reflect that information here. So I'm going to move, let's see, in the first unit of time, these things moved 1 box down. In the, after 2 units of time, they will have moved 4 blocks down. So I'm going to move these guys to 4 blocks down. And then after the next equal interval of time, they will have fallen to 9 blocks down. So let's move these to 9 blocks down. And then in the next unit of time, they will have moved to 16 blocks down. So let's move this down to 16 units down. Okay, so here's what we have. We now have where these objects are. And this is supposed to represent the same object that we're looking at in 3 different ways. So where this object is after 1, 2, 3, 4 equal increments of time. All right, now what we'll do is draw some vectors to represent a few different quantities. 1, how fast the object is going. 2, the force acting on the object, and 3, the object's acceleration. All right, so velocity. At the beginning, right, we're going to assume that v naught is 0. So we don't have to draw a vector at this first instant to represent velocity. But after the first increment of time, here's what I'm going to say. Let's say that it's moving with a speed v. All right. The question is, in an equal increment of time, how fast is it going? So after time t, it's going with a speed v. After time 2t, it's going at a speed 2v. After time 3t, it's moving at a speed 3v. Now, this is going to screw up a little bit, but I guess maybe I have room. And after 4 intervals of time, it's moving at a speed 4 times as fast. And that, if you think back, jives with the idea that, what does constant acceleration mean? Well, it means that velocity changes by the same amount during each equal increment of time. So this starts at speed 0, and during every time interval, we have a change in velocity of v, right? 0 to v is a change of v. v to 2v is a change of v. 2v to 3v is a change of v, and so on and so on. And because that object gets faster during each equal increment of time, it goes farther during each equal increment of time. Okay? Now, the force acting on the object. Remember, gravitational force. And really, it's an object's weight. So what does this object weigh? I don't know. It weighs whatever it weighs. Fg. And then here, it's still Fg. And here, it's still Fg. And here, it's still Fg. Now, I'm doing not a great job of making these a nice standard length. Now I am. I'm making them about a block and a half long. And now, it's important to know that from here to here, the scale is totally different, right? A vector this long here represents a certain speed. A vector this long here represents a certain force. But this real important, is a constant gravitational force. It doesn't change at all. And remember, that constant gravitational force gives us a constant gravitational acceleration. So here I made this vector that long, which is like 2.5 blocks, and that's totally arbitrary. Why did I make it 2.5 blocks long? I don't know, because I felt like it. And after this next amount of time, well, it still accelerates at the same rate. It still accelerates at the same rate. It still accelerates at the same rate. It's still 2.5 long, accelerates at the same rate. So the force, and therefore the acceleration, remain constant. And that constant acceleration, remember, gives us a velocity that increases at a constant rate. And it gives us a position that increases quadratically. Okay, fair enough? Okay. Now, we could do the same thing here. I guess why not? Why wouldn't we? Let's do a few fewer of them. Let's do or maybe not fewer. Let's see, 1, 2, 3, 4. Yeah, I'm having a yeah. You know what? Let's just move forward, okay? All right. One big deal for free fall. All right, what we call free fall. Really, the only criteria that has to be met is that gravity is the only force acting on an object. All right, typically, what we'll do is neglect air resistance. All right, air resistance, well, changes gravitation. Well, changes the acceleration that things have when they're in free fall. All right, but typically, in almost every problem we do, we will neglect air resistance. All right, but here's a super duper important thing. Regardless of what direction an object's moving, or how fast it's moving, or where in what we call its trajectory that it is, if it's thrown up, thrown down, just plain old falling from the top, if it's doing any of this stuff, acceleration due to gravity that we call G is 9.8 meters per second squared downward. Doesn't matter how fast you're going, doesn't matter if you're moving up or down. If an object is in what we call free fall, its acceleration is 9.8 meters per second downward. Okay? Okay. So, here's what I'd like you to do for the next time I see you. I would like you to draw a velocity time graph for these three situations or cases. One, an object is thrown upward and caught while it's on the way up. Two, object is thrown downward and caught on the way down. Three, object is thrown up or caught on the way down. And what you have to do is, for all these, only plot the free fall part. Right? When I say something's thrown, don't graph the part where it's in my hand or in someone's hand. All right? Don't graph the part where it's caught, because that's not free fall. When something's caught, well, then your hand is exerting a force or whatever catches it. All right, so just plot the free fall parts. And let's also make the following assumption. We're going to call up the positive direction. Okay? You come back with these graphs sketched. I don't need numbers. But it should have there should be something very common about all three. Okay? Okay, see ya when I see ya.